So here we have the fundamental theorem of calculus. F of x is a continuous function on a closed interval. Then the definite integral from a to b of f prime of x dx is f of b minus f of a. Usually we phrase this differently. We say the integral from a to b of f of x dx. We kind of focus on the integrand. And then we suppose the creation of this antiderivative, capital F. So usually we say the integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of f of x. That just means capital F prime is little f. So if we integrate a derivative on an interval, we evaluate the function at the endpoints. Integrate a derivative over an interval by evaluating the function at the endpoints. Integrate I just realized why I did not want to write this all down here, because I wanted to write this up here. Oh, well, you know. As usual, if you had a professional teacher, they would have planned this out, but you all are stuck with me. Here we are integrating a derivative over an interval. And we do that by evaluating the function at the endpoints. Evaluate the so to integrate the derivative over an interval means we're going to evaluate the function at the endpoints of the interval. And here's what we want to highlight. We want to look at the endpoints of the interval and recognize that as the boundary of the interval. This is the way we want to view this moving forward. We want to view the endpoints of the interval the endpoints of the interval form the boundary of the interval. So we're integrating a derivative over an interval by evaluating the function at the boundary. Since it's an interval, the boundary is just the endpoints. Integrate a derivative. Integrate a derivative over some region means we evaluate the function at the boundary. This is super hand wavy. I shouldn't even be recording this. It's like saying 1 divided by 0 is infinity. I'm just kidding, it's just super hand wavy. We're integrating a derivative over some region, and all we have to do is evaluate a function at the boundary. This is the bird's eye view, the very hand wavy description of what we're doing with in integration. And this is kind of the template that all the fundamental theorems fit into. Fundamental theorems are variations on this theme. We have just different forms of what we count as a derivative. But we want to integrate a derivative over some region, we evaluate a function at the boundary. If we want to integrate, say, so if the region is a region in R2, an area, we're going to be evaluating the function around the outside. So if the region is a circle, integrating over all the points inside of a circle, we're going to evaluate a function at the boundary, the circle on the outside. If the region is a solid sphere, then we're going to be evaluating some function at the shell, the outer boundary of the sphere. We didn't frame this way in single variable calculus because all we had to work with when we're integrating is an interval. We're just taking a bunch of points, plugging them into the function and adding up the values. The only collection of points that makes sense to do this in one go is an interval because we have a function of a single variable. So our boundary is just left end, right end, lower bound, upper bound. That's all we really got. So it didn't really make sense to look at that and say, this is the boundary of an interval. We're integrating a function over an interval. That part kind of fades into the background. But now we want to highlight that aspect of it moving forward. So this is the thing we want to think about. When we're integrating a derivative over a region, we're going to be evaluating the function at a boundary. If that region happens to be, pulling my whole desk out of place here. If that region happens to be an interval, then the boundary is just the endpoints of the interval. The other thing that we want to recall about evaluating integrals is that we're just adding up values of the function. So the other thing is that integration is just addition. The integral from a to b of, I'm going to just try to be consistent, of f prime of x dx. Remember that this comes from a Riemann sum. Going to infinity is where we switch over from a discrete sum to a continuous sum. And this is just going to be the sum as n goes, do I use n? N goes from, as I, because it's the index, as I goes from 1 to n. We're just evaluating the function at a bunch of points and using that value for a little while, assuming the function is constant for a little while, and then adding up all those areas. This is just areas equal to length times width, but the length is all variable, so we have to switch to addition. And then the calculus part comes in by taking the limit as n goes to infinity. Now we have switched from a discrete sum to a continuous sum. We're just adding up values of the function. We're just adding up a bunch of values of the function f prime of x. Evaluating the function at all the points on the interval and adding up those values. We want to think of adding up values of f prime at each point in the interval. That's because integration is addition. This is the way we think about integration. This is the way we want to think about the fundamental theorem of calculus. We want to think about the fundamental theorem of calculus by integrating a derivative over a region by evaluating the function at the boundary. Part 2, we want to think about integration as addition. We're just evaluating the function at all the points on the interval, subject to some weight that's getting smaller, but evaluate the function at all the points in the interval and then add up those values of the function. That's the definite integral. Sitting on top of that, we're also thinking of taking this discrete sum where I equals 1 plus 2 plus 3 plus 4 up to n, and saying when n goes to infinity, going from our discrete sum to a continuous sum. And this is where the wacky things happen. Because here, there's a next term, I equals 1, then the next is 2, then next is 3, and so on. But now, we're in the definite integral, we're adding up over a continuum. We're adding up over all the real numbers, and there is no next real number. So that's the crazy stuff that's going on here. There is no next real number. There is a next integer. There's no next real number. Any questions? So much going on in our wacky notations. Let's pause the video here and talk about the kinds of things that we're going to be integrating.